Good afternoon, everybody. Hopefully you have a sheet. You're going to need to take a few notes, though, that won't fit on the sheet. So make sure you have some room for some notes elsewhere. There's a fair amount of information that we are going to give you up front. Try to wrap up the conversation so we can get started. We got lots to talk about. So hello again. Today our topic is on titrations. Titrations, the term titration, I understand, comes from an old French word that actually has to do with, at the time, this is like 16th century, understanding and sort of analyzing the purity of gold and silver in metals and coins. So back in the 1500s, when gold and silver coinage was a pretty big deal, the purity of those things was studied and described using a French word that is the root of titration. How pure the composition of something very important to them at the time was studied and put to a number. How pure is this gold coin? How pure is this silver coin? And the word that gives us titration today had to do with that study for understanding the composition of those things. So titration today isn't going to be about silver and gold. We have, let's say, far more efficient ways to study silver and gold than anything as complex as titration. But it's still a very important skill that you're going to hear a little bit about in terms of career places it's used. Titrations are being done right now somewhere in Bismarck, Mandan. There's titrations happening every day, all the time, in some lab somewhere. There's a reasonable chance that depending where you head after your life, if you take a science lab in college, and many of you will, unless you get it out of the way with an AP course, in which you'll probably be doing a titration here. You're going to see a titration at some point. Maybe not like an earth science class, but most any other biology, chemistry, biochemistry, nat phys, there could be some titration brought in. It's all over the place. So titrations, if you were here in my class, classes, you've kind of already been told to watch a video that talks about the setup, but there's a lot more description here. So if you've taken those notes already, you can add to them. If you haven't taken those notes, you still need to watch that video and get the pictures in. You don't have to try to keep up with it today, but you want to have that for your next class in my Thursday, Friday class in my sections. In the case of everybody else, perhaps you haven't seen this stuff yet in our class this year, we're going to give you some content on titrations and some terms. If you want to try to sketch it, you certainly can. We'll post a link to the video that I'm talking about that puts these pictures up again, but doesn't necessarily include all this information. So there's a lot of parts of titration, how it kind of goes, and it takes some description because there's some vocabulary and technique that go with it. So what you see here is the setup for a titration. Before we get into the setup and start talking about the actual physical technique of it, like what's the point of a titration? The idea is that titration is used to figure out something that we don't know using something that we do. And we use that a lot in other places too, but we use what's called a standard or a standardized solution. So we know, we'll say, everything about that solution. We know what's in it. We know exactly how much is in it in terms of molarity, moles per liter. Right? We know exactly what's in there. And usually it's lots and lots of decimal places. It's lots and lots of significant figures. This gives us a great foundation for our work. So we start with a standard. The standard is usually something we purchase or something that we've standardized in advance, and that takes kind of a pre-lab. In AP Chem, we standardize our own analytes and kind of titrates, and we kind of go from there. In our class, we'll do titrations in class in the next week and a half, perhaps, where it won't be something you'll have to do with advance. But we take a standardized solution and we use that to figure out something we don't know about the other solution. So in this picture, I don't know if you can tell, but there's a liquid in that tall, skinny, what's called burette up top. And then there's a liquid in that bottom flask. Those are two different things. And we're going to use the one that we know about, which is in the top skinny burette, to understand what's in the bottom one, where we don't know everything about it. And what we don't know about it, typically, is its concentration. Exactly how much is in it. We're going to analyze that, and so we call that the analyte. You see that in the pictures. It's what's being analyzed. So it's called the analyte. That's the stuff we're studying and trying to learn more about. We know everything about the top one. We're trying to figure out more about the bottom one. The classic titration, most people in life, their first time are titrating anything, is an acid-base titration. Just a simple acid with a base. And we use an acid that we know about to study a base, or we use a base that we know about to study an acid. One way or the other, we can analyze one with the other. And they cancel each other out chemically, so we can use one to quantify or put a number on the other because of how they cancel out. You're going to see a little bit of that today. In AP, we do a redox study. So we use oxidizers and reducers. We study in a lab there, for example, the concentration of something like a bottle of hydrogen peroxide that you might buy at the counter at a drugstore, or you might have in your cabinet at home. And that's not an acid-base thing, it's an oxidation reduction. There's lots and lots of other places where titrations show up. So for example, use it to sort of understand more about microbes and how much is in a sample, a solution of a rock or something, where microbes are involved because of their population and their activity can be measured based on chemicals that are involved. Now Mrs. Arnold's worked in titrations and lab settings that are a little bit more specific and just kind of broad strokes. And she's going to tell you a little bit about some of the stuff that she's worked with and has experience with that you might end up seeing in your own life too. Take it away.
So some of you know that I've not always been a teacher all my life. I also was a med tech, and I worked for the University of Wisconsin hospitals and clinics. And what I did there was I worked with solid organ and bone marrow transplantation. So how many of you have your license? How many of you are organ donors on your license? So I was the lab tech that was in the lab. Say there's something unfortunate that happens to you or one of your loved ones and you are an organ donor on the back of your license. I was the lab tech in the lab that did all the stuff to make sure that your organs and your family's wishes were met by matching it. And it's based on immunology. So when we talk about this idea, you had to grow stuff. You took cells from the donor, you took cells from the recipient, and you had to grow them in what was called a medium. Do you have a pH by which your metabolism optimizes? Anybody know what that pH limit is for the human body? 7.35 to 7.45. That's where your blood likes to stay, and that's where your body likes to stay to maximize everything, including fighting infection. So that's kind of what we had to do. We grew those cells, we put them in a plate, and then we would look at them to see if the recipient would be okay with these donor cells. And by visually looking at it, which we're going to show in a minute, you can visually see the difference in the pH. And if there's an explosion of cell growth from the donor or the recipient to the donor, we can tell visually that that's not a good match. And we can report to the transplant surgeon and the transplant team that this is not a good donor. In Bismarck, we have this situation right now, possibly. We have a beloved colleague who has been diagnosed with leukemia. We don't know where it's going to go. He possibly might need bone marrow donors. And what I described is what's going to be probably done in Fargo, or if he needs to go to Minneapolis, because that's where the donor centers are, they're going to take all the blood of all their donors, including his family, they're going to test them in a little medium, and they're going to see how it does. And you can tell by pH just by looking at it if it's good or not. And when you're talking about a kid or when you're talking about an adult that has children, you want to know those results pretty fast. So we can come up with a prognosis, we can come up with a plan, and we can help that individual. So that's kind of where you see this. Another place is Alderon out of Fargo. They make plasmids, and they use plasmids for what's called transmutation in bacteria. And they are a global customer. And again, growing media to grow these plasmids to sell them internationally. So that is a homegrown in Fargo out of North Dakota, and they're doing really, really well. So those are two applications of this.
Ms. Arnold just said something about being able to visually see the pH of something, and we have an example of that here. In here she has acetic acid, it's a 0.5 molar NaOH. She's told me that she's put the phenolphthalein in here.
Phenolphthalein is...
So yeah, go ahead.
It's like a big molecule, a big complicated molecule that when you add an acid or a base to it, changes its structure. And when you change a molecule's structure, it affects how light scatters off of it. And so if it scatters in a certain way, you can't see it. And if it scatters in a different way and some colors are being absorbed, then you can't. So we're going to see that when we change the pH in the solution here, that the phenolphthalein, which right now looks like water, later when it's a higher pH won't.
So what color is this right now?
Clear.
It's clear.
Phenolphthalein, the big, Scrabble, bazillion point word.
Clear.
Excellent, thank you.
We have a clear solution.
So Ms. Arnold's going to add some sodium hydroxide to this solution. Now, when she adds the sodium hydroxide on, she's changing the pH of this solution.
We're going to put a base in there, jack the pH up. I don't know if you can see that on the light a little more. You start to see when she drops a drip in there.
Oh, pink, that's pink.
It starts turning a little bit pink, and then it fades away because there's still a little bit of acid in there. Drop it in there.
You have to.
Now the pink stain.
So a slightly pink solution means you've taken all the acid out by adding base, and if you keep adding more base, it'll just get pinker and pinker and pinker. So you can visually tell.
I want to take it back.
You can visually tell when the reaction is complete because it's going to be pink. And you're going to see that in lab yourself. A very similar kind of thing.
You ready?
Change pH here.
Pete tells me that this is base.
Beige.
It's base, so what am I gonna add to bring it back?
It's end of the year. No. Put some acid in there. Goes back, and it'll go back and forth all day long. So that sweet spot in the lab is going to be the first moment that it changes pink and stays pink. You'll know that when you get there. We'll show you a video here in a few minutes that sort of shows that final drop. And it's amazing. One drop makes it do nothing special, and one more drop makes it do something cool. So it's down to the end where you want that perfect amount and no more if you can help it. The perfect amount is not easy to accomplish, but it's a titration.
Yeah.
A lot of you are going to find it very
In the
satisfying.
room when I was fighting with that, remember? Yeah.
Getting it right is the first time you do that is super satisfying. Until then, it can be like very tedious, but super rewarding.
Whose fault was it that I went over? Tomas!
So we're going to talk a little bit about how the setup will go, and we'll guide you through this when it comes to the lab too, and put these up for you to kind of follow through with us. So if you want to just listen along, maybe right, for the technique part, the setup part. So you kind of imagine doing this yourself. We're going to start by filling that tall burette with the good stuff, which is the titrant that we know about. We usually rinse it first. Unless it's going to be prepped from a previous class, you might be asked to rinse it with a little bit of the stuff first. We do that in case there's anything else in there, a drop or two of water from when it was cleaned or something. We want to rinse that out and rinse and leave any residue that's in there. Let that be the stuff that you're going to be using anyway. So it's kind of like pre-coating it a little bit in case there's anything left from before. That could be a problem, changing that. We don't want to have anything left in there that's not what we're trying to study. And then we fill it up to the top. So basically you can see here it's pretty well filled. It says around 0 milliliters. So up near the top, so you'll have enough for the reaction to occur. And then you want to drain a little bit out. So you can see a little red valve down near the bottom of the picture there. You turn that little valve, and it's actually in the open position right now, it looks like to me. And all that liquid would start running through very slowly. What we want to do is drain a little bit out to make sure there's no air bubbles in there. So in your lab, make sure you drain a little, get your air bubbles cleared first. Because an air bubble will throw off all your measurements. At that point, once you've drained the bubbles out, now we go ahead and be ready to put our flask under. So you wouldn't want to drain those into the container you're studying, maybe into a different container, even just in the drain. And then we make our first volume measurement. You can see up at the top, that's pointing to the initial volume reading. Burettes are a little funny because the 0 on a burette is up here. We get used to 0 being down here. We've got a graduated cylinder on a beaker. 0 is up on the top. And then the numbers count. The bigger numbers going down to 50 at the bottom. Because we drain, we start at 0, and we can measure how much we've drained out then from the top down instead of from the bottom. So you're going to make your first volume measurement. Then we get our flask ready down below. We're going to use a flask so it swirls a little easier, it doesn't splash out of there as much. We're going to put the stuff we're trying to study in the flask. So in this example you just saw demonstrated, there was originally some acid in the flask, and we added base to it. So we put acid in the flask, or whatever it is you're studying. Measure that really carefully, and make sure you write it down. Because we want to know how much we've got in there. In the math, you have to know your volume is super duper precise. A couple drops of an indicator, probably phenolphthalein, like this one up here with a pink, so that we can see things. We're going to add and drain. You can see there that we're now later, the drain has occurred, the liquid is lower in that little steam burette. And now the solution is very good. Now, it shows in this picture the flask is being full. We wouldn't use it that way. You want a flask that's big enough so you can swirl it. You can't mix it. But it helps you see it's going to be pink. So we're going to use a big flask. Once you've reached the end point, that means it's pink. Just the first time it gets pink, it stays pink. So usually the idea is you add it gradually and then slowly add a drop at a time until the color lasts for at least, say, 30 seconds. But gradually over time, the pink will fade away again because the CO2 from the air gets in there and makes the solution slightly acidic again. So if you left it open overnight, it would clear out again because you're adding in carbon dioxide to re-acidify it. Also why tap water if you do the glass out overnight is funny the next day acidified. We're going to show you a video that kind of explains how that would go and how that would look. But at the end, you make a total final volume reading, write that down, and then we compare that to the number you wrote down before. Okay? to figure out how much was used, how much did you dispense or drain out of your burette. Because that number, typically, as I sort of hinted at here, circling that, that's going to be the first number you use in a lot of these stoichiometry problems, like the ones that are in front of you. When you start doing math, we're going to start our math using that volume more often than not. And it's found by looking at those two different measurements and subtracting. You should be able to find 2 decimal places on most of the measurements that let's say all the measurements you take on a burette should have 2 decimal places. If you're not writing down 2 decimal places, or the person in your lab group says, oh, here's 2.3, don't just take that. It's got to have 2 decimal places. So these burettes, you read the first, let's say 1.25 milliliters, and then you drain some out, and at the end it would say 3878. We can simply subtract and find out how much was used. So it's the difference from start to finish, and you can tell by subtracting then how much was dispensed. And that black 37.53 in the corner would be the number I would use from then on. We're going to watch a video of this, show you how the last few drops kind of look, and it will explain some stuff along the side as well. This is a close-up of an actual titration that we did a couple years ago. This was done. You can see it's actually right outside my classroom door. Okay. Dropping a drop in there. Just somebody that were a little further back during the demo didn't necessarily get to see this. And Mr. Mitchell hinted earlier that this might be a little jerky because it's projected through and used right. So we should have that. Anyhow, get the idea. You're going to add a drop in. It's going to be a splash of pink as it mixes into the solution. That pink will fade away. Pink, in this example, pink means that's basic. That means the base is still there. It hasn't been canceled out or neutralized yet. Every time you add a drop, you're using up a little bit of the acid molecules that are in there. And our goal is to use up exactly all of the acid molecules, but no more than that. Don't add any more than it takes. So it says here, you're going to see as we go, the pink will last a little bit longer every time you add a drop because there's less and less acid left in the flask to cancel it out. And as we do that, the pink will last, it will fade away more slowly. And when you start seeing your pink last for a second or two, that's when you want to slow down for one drop. So there are acid particles in the acid, base particles in the base. And we're going to look at those equations that will be up here in just a moment. We may pause it actually at that moment and ask you to write that down. When you mix an acid to the base, you make water molecules, but you also make what we call in chemistry a salt. Now it's not salt like you put in your food all the time, but it's a salt. And those salts are very soluble typically, so they dissolve into the water, and you can't see them, but they're there. They're the other product. And there's our equation. Maybe we'll pause it here. Let you jot that down.
I want you to look at this equation. This isn't a balanced equation of sodium hydroxide and acetic acid. In the equation, what's our molar ratio of acid to base here? Go ahead, Reman. 1 to 1. So that's super important in this reaction that we're showing you, is that you understand your molar ratio of acids to bases. Because when we go to do the math on this, knowing that molar ratio is really important.
Can I ask a question real quick?
Yeah.
So in that class, that was sodium hydroxide and acetic acid. And I put in, to make it pink, 5 drops of NaOH. So how many drops do you think required me to put in of the acetic acid to bring it back? 5. So that's what? Thank you.
It's 1 to 1. And as long as you're using equal concentrations of those, it stays pretty much 1 to 1. You can add 5 and add 5 to the other one. It just flip-flops back and forth. And in your lab, the goal is you're going to know how much, what the molarity of one of those two is and not the other. So we need to figure that out in the math, but that's exactly the idea. Most titrations that you'd ever see, at least in first year chemistry, will be a 1 to 1 ratio. You can do titrations that are 2 to 1 or 3 to 1. We're going to pretty much stick with a 1 to 1. So that's a base plus an acid mix. You can see water over there. That other thing, that nacho-looking thing, is salt. A salt. It's sodium acetate, but it's a chemical salt. By definition, that's just the other stuff when an acid meets a base. All right, let's finish it up. Last couple drops are coming up here in the flask. Again, as we go, the pink will subsist a little longer. I think I put in the video here, watch when we get down to that dragging kind of delayed drop, even though it's a little bit leggy right now. When you're doing this in the lab, you want to get a feel for how to handle that little valve so that you can let one drop out at a time. That is the hardest part of titrating, is being able to gently open the valve so you let out just one drop. So let's watch this drop. I say here it's going to last a little longer. It starts to spread out a little bit before it finally fades out. And when you see that pink that starts to spread and then kind of shuts down again, that probably means you're one drop away. And in this video, the next drop. That's how it's going to work for you. Now that solution stays very pink. Any pink you can see that doesn't fade away counts. It doesn't have to be this way. The faintest pink means you actually did it almost like you got it to the nearest half of the drop, which you don't do. It kind of takes a little luck. But if you get that pink, that means you're done.
And I always say too, the color of the pink doesn't matter. I mean, the color of the pink can depend upon a lot of things. What you need to know is the point in which it goes from clear to solid pink. And you need to know the drop that it happens. That's the most important thing. The color of the pink isn't important. You just want to know when it went from clear to solid pink, regardless of how dark.
So that's the moment when you stop adding more drops and you can make your second volume measurement. So I take the first measurement, you drain down, it turns perfectly pink like that, you make your second measurement. And then we subtract those two to get our amount dispensed. So that's kind of the idea. I think there's not much really more here. We'll show you the side by side real quick, I think. If I remember. All this gets into kind of titration math, so we'll leave it at that for this. Mr. Mitchell's been working on a problem or two.
Now,
If you were here last week, Mr. Mitchell's back on the
he let me play with
on the tablet.
Oh, yeah.
He said he wouldn't even come to large if I didn't let him
It's the
today.
only thing that's making my day somewhat positive is Mr. Blackman.
And all of you fun people. If you weren't here, he'd have no reason to be up here playing on this, but he probably would anyway.
We'll see.
Okay.
Okay, Mr. Blackman, I mean, you can approach these a couple of different ways. We approach them differently not because one way is right or wrong. We just approach them a couple of different ways for a couple of different reasons. We thought it was important to show you guys how to do each of them because sometimes you pick it up easier doing one way versus the other. So the most important thing to all of this is that one-to-one molar ratio. So when you see a problem like this, you have to understand that the moles of your acid and the moles of your base need to be equal to one another. Okay? Now, when you're finding moles of a solution, I'm going to think back to our old equation of molarity is equal to moles over liters. We never really agree with me on that one. Moles, then, is going to be equal to what? Molarity times liters. Or your molarity times your volume. Okay? I like to go liters because that's going to give you correct, because molarity is moles. So to find the moles of something, you're going to take the molarity times the liters to find the number of moles. And I found in the last couple of years when I started doing these, the easiest way to kind of set all this up is to separate it into two columns where you have your acid and you have your base. If you want to show one is your titrant, one is your amide, you can do that too. And then I write a line for molarity, liters, and moles. I do that for both. Molarity, liters, moles. Then I read the problem. It says the known concentration of NaOH is 0.5 molar. So is NaOH your acid or your base? Base.
How do you know? How do you know?
Yeah, I don't know that I've gone over that.
I haven't. How do I know NaOH is my base?
That's not my acid.
Ah!
I get that answer a lot. That's what people say.
How do you know it's an acid? How do you know something's an acid?
Formulas of acids always start with what?
Begins with H.
H.
So what does NaOH end in? OH. So anything that's a base is an OH.
For first year chemistry problems, any base will end with an OH. So we've got an OH on the end. If you think about H from an acid and OH from a base makes HOH, which is water.
So I have, yeah, sorry. 0.5 molar base. If 30 mils of this solution are needed to titrate, so 30 mils is 0.03 liters, are needed to titrate, react, and neutralize 35 mils of acid. So over here, then I put my 0.035 liters. Okay? That's what I know. This is, what is the concentration? The acid. The other thing that I know is that when I reach my titration point, so when it says, where's the key term here? Are needed to titrate, react, and neutralize. When I see that needed to titrate or neutralization reaction, I know I have a 1-to-1 molar ratio of acids and bases. Now, can I solve for moles of base here? I can just take 0.5 times 0.3. How many moles of base do I have? 0.15 moles. Agreed? 0.015 moles. Is that better? Thank you for keeping me honest.
So he's plugging in stuff to that bottom left equation. Moles equals molarity times liters.
Right.
Make sure.
Molarity times liters equals moles. My moles is 0.015. What's my moles of acid? 0.015. If I know moles and I know liters, can I convert to molarity? How do I find the molarity here? I take 0.015 mole over my 0.035 liters, and my molarity, according to Mr. Blepp's calculation, I'm assuming is correct. Or is like that here, that's right.
Sig figs. It's 0.42.
0.42.
It needs to be one sig fig, but 0.42. How did we know moles were moles, right? So we knew that the moles on the right were 0.015 because he had the two numbers to multiply, and that gave him 0.015. We bring that across because we've got a 1-to-1 ratio. That means moles of one is going to be equal to moles of the other. That's what titration is goal of doing. Is getting equal moles of acid and base in the flask. Because when you've got equal moles of acid and base, then you've got a perfect stoichiometric 1-to-1, and you can neutralize it just right. So if you know moles of one, and we know it's a 1-to-1 ratio, then you know moles of the other are exactly the same. If it's not a 1-to-1 ratio, we've got to tweak that. But generally speaking, you're going to look at 1-to-1 ratios, maybe an occasional 2-to-1 ratio.
We're down, you want to show your method once, and then we're down to 5 minutes. You're going into another.
So if we're looking at this as a stoichiometry kind of situation instead, just real quickly, I've got acid with base to make water and salt. And we're going to assume it's a 1-to-1 ratio until we're told otherwise. So I'm going to assume this is 1-to-1. I don't even know what these formulas are, because it doesn't tell me in the problem what my acid's formula is, so I can't really write an equation, but I'm going to say it's a 1-to-1 ratio, and there's kind of a balanced word equation, which we don't often give you. We'll let you get away with it. But we're going to do it here. So I've got a balanced 1-to-1 ratio. I'm going to solve this as I know it's set up as a stoic problem. In case you really like stoichiometry setups and you're super comfortable there, this will help you out. Okay? So I'm going to start with what I know both things about. And right here I know about my base. KOH is my base, I know its volume, and I know its molarity. So I'm going to go ahead and start with its volume. There's 15.5 milliliters of base. I'm going to convert that to moles using stoichiometry. And according to my molarity here in the problem, there is 0.215 moles of base. And you can write it as KOH if you'd like, but I'm going to just go ahead and remind you and emphasize that that's a base. For every 1,000 milliliters, remember, anytime you see a molarity like this, that's moles per 1 liter, or moles per 1,000 milliliters. So that's why I'm writing that ratio as I am. The next step is to use that mole to mole ratio like we do in Stoic. And according to my problem, there's 1 mole of base in the equation for every 1 mole of acid. There's my 1-to-1 ratio that we keep emphasizing today. And that's as far as I can go because I don't have necessarily the next piece of information, which would be the molarity. That's what I'm trying to find. So for this one, I'm going to punch this in, and I'm going to get moles of acid. I didn't bring my calculator, so let me punch the mole of acid. Unless someone's got it from 15.5 times 0.215 divided by 1,000, and the ones don't make a lot of difference. This is 0.00333 moles of acid. And I need molarity. Mr. Mitchell mentioned earlier, molarity is moles per liter. Well, it says here we used 21.2 milliliters of the acid, so that's my volume. I'm going to put that in down here as liters. Again, move that decimal over thrice. 0.0212 liters. That's just a milliliters to liters converted. So if we divide that by 0.0212 liters, we get a molarity of 0.16 or so molar acid, moles per liter acid. And that's a stoichiometry way of doing the same thing Mr. Mitchell did. Now, they're very different. If you like the table way Mr. Mitchell has, do it. If you like the stoichiometry way, which is exactly the same math, just laid out very differently, you can do that. And there's actually one other way that's kind of sloppy lazy we don't have to teach you, so you probably won't.
Sloppy lazy.
But probably stoichiometry is pretty familiar, and I've seen a lot of you using that in the lab this week, so that's where I would go, but it's completely up to you as long as you get the right answer. Your last large group full of content is complete. Actually, our final large group, we'll see you then. Should bring a Kleenex to
We'll make your world a better place. Legacy High School. So you're going to get 2 compounds. I'm going every minute in paper at a study session. No, 4 hour study session. But no, but I have to No, yeah, I don't care. I feel guilty letting him go. Jerk. He was telling me. It sounds like he did really well. I just haven't seen the collection. I'm so mad that I didn't do a better job of going over the fact that on a satellite, you're seeing triple forces gravity. And that satellite moving like this, the brute force is going down. They didn't recognize the force of these gravitational force. 4 years not down. Yes, because they're so used to drawing force diagrams at the surface of the Earth. The force gravity goes straight down on every force diagram they've ever drawn. And now all of a sudden they throw a satellite in there, and your force of gravity is directed toward the Earth, which is a different object. Yeah, I've used that in the past. We'll let them get there eventually. I gotta come out and meet that dude. Did you talk to that guy yesterday?
What guy?
Eggers?
Yeah,
How long was your meeting?
20 minutes.
20?
Yeah.
Who's Eggers?
This guy from,
How was it?
he's from a college in California that they have a research group that goes out and does research on the college ratings program effectiveness for them.
Oh, okay.